Well, hello everyone, and welcome to Prep 9. So in this prep, we're going to introduce the t-test. Previously, we had worked with the z-test, and the deciding factor on when you use a t-test is whether or not you know the population standard deviation. If you know it, then stay with a z-test. That's what it's designed for. And if you don't know it, and it wasn't given to you in the problem, then you go for a t-test. So when we're reading these problem descriptions, what we really have to decide is what's the population and what's the sample, so that we make the correct choice. So let's look at the first one. The quality control department of a paperclip manufacturer periodically tests the quantity of their packages. They want to verify that the packages are being filled to the advertised quantity, which is an average of 250 paperclips. So that's the population. What you advertise is your population. They take a sample of 30 boxes to determine if they are being over or underfilled. They find that the 30 boxes have an average number of 251 paperclips with a standard deviation of 0.8. So these last two sentences are all about the sample. So, for the population, all we have is the mean, the 250. For the sample, we actually have a lot of stuff. We have n, the number of boxes. We have 251, which is the mean. And we have 0.8, the standard deviation of the sample. So which test do we conduct? Well, we don't have the population standard deviation, so that means it's a t-test. And what's the direction of the test? Well, we don't know if they're being over or underfilled, so it's a two-tail test. All right, next one. Kroger knows that historically the average customer spends $52.53 on an in-store purchase with a standard deviation of 28.29. Okay, that's the population, right? Anything historic is the population. And we're given the standard deviation, so we immediately know this is a z-test. Kroger wants to test, workers have noticed that pickup orders tend to be more expensive, so the word more gives you the direction. More means greater than. Kroger wants to test this observation using statistical analysis. They take a sample of 100 pickup orders from the past 3 months and find that the average is 70.21 with a standard deviation of 24.56. So the direction of the test is one tail to the right, because we're testing to see if it really is more. Okay, and I'll let you answer the last two. But remember, all you have to do is figure out what's the population, and then if you have the standard deviation of the population, it's z, and if you don't, then it's t. All right, so these next 4 tabs are all t-tests. So here we go. A manufacturing company reports that the average number of units produced per day is 80 units. Management tests new machinery on one of the production lines to see if they should convert all the lines to the new machinery. They collect data on the number of units produced per day by a sample of 30 employees, and the results are provided in the Excel sheet below. At the 0.05 level of significance, basically 5%, is there enough evidence to conclude that the average productivity has changed from 80 units per day? So, this is the new sample, and the population we're just going to call the old. So the case here, what we have to decide has changed. So all we're after is, has it changed? Changed means two-tailed, because we don't know if it's bigger or less. Distribution, I mentioned that all these problems are going to be t. The null hypothesis is that there's no significant difference, and the alternative hypothesis is that there is a significant difference. Okay, now the new X bar. So X bar is going to be the average of all these guys. And the standard deviation, it's going to be standard deviation about S, because this is information about the sample. And N is equal to the count of all these guys. All right, now we get to degrees of freedom, and we have a big note here, so let me read it and take you through it. So degrees of freedom refers to the number of independent pieces of information that are free to vary in a statistical calculation. It's essentially the number of values that have the freedom to change without affecting the overall result. So here's an everyday analogy. Think of it like this. Imagine you're planning a family budget. You have a fixed amount of money to spend each month, let's say $1,000, and you need to allocate it across 4 categories: food, housing, transportation, and entertainment. For the first 3 categories, you can freely decide how much to spend. But once you've decided on those 3, the amount for the 4th category is automatically determined. In other words, whatever is left over. In this scenario, you have 3 degrees of freedom. You can freely choose values for 3 categories, but the 4th is constrained by your previous choices in the total budget. In a t-test, we are estimating population standard deviation from the sample standard deviation. Once we make that estimate, we can at most change n-1 of the sample values, since the last value will have to compensate to produce the same estimated standard deviation. So what's the practical implication? The practical implication is that our test is a little less precise because we're estimating. This is accounted for in the shape of the t-distribution with fatter tails than the z-distribution. And the tails are fatter, especially when the sample size is small. Once sample size gets big, meaning 30 or more, then the t and z start looking very similar. Okay, so degrees of freedom here are going to be n, so we'll put equals n, and it's going to be -1. We lose a degree of freedom. All right, the old mu given in the problem is 80, and the old standard deviation is not given in the problem at all. We don't have it, so we have to substitute the sample standard deviation, which is this one. All right, the sampling distribution of the sample mean, what's its mean, is always 0. Well, you hope it's 0. Sorry, no, I got that wrong. It's always the same as the population mean, so it's going to be equal to the population mean. There we go. And then the standard error is going to be S. Remember before it was sigma, but now it's S because we have to estimate it, divided by the square root of n. There's our standard error. And here's our curve. Now, looking at the curve, we can probably figure out if this is a reject or not. And as you can see, we are more than 2 standard errors away from the mean, which usually means it ends up being a reject. So let's see if that's true. So the observed difference in means is new minus old. So there's the new mean minus the old mean. And then the percent change in means is going to be equal to this observed difference divided by the old. So it's a 1.5% change. Doesn't seem like a lot of change, but who knows, maybe the units are expensive to produce. Okay, and then the t-score is going to be the observed difference divided by the standard error, and here's our standard error up here, 2.68. And what's the probability of a t-score of 2.68? So we have to see table below. So in this table below, it's the same table we had before with the z's. Now we've added one more column for the t's. And in the t's, you have to figure out if you're one-tailed left, right, or two-tailed. And then if you're two-tailed, if you're positive or negative. So we are two-tailed we are two-tailed and we're positive because this is a positive number. So we look at two-tailed positive, and the formula is t dot dist. It's actually really nice. It's a lot easier than it used to be with the z. And it's going to be t dot dist, dot 2t for two-tailed. And then the t, and then the degrees of freedom. There, 1.21%. So now we actually do know that pretty much we know that it's a reject because that 1.21 is less than 5. But let's go ahead and throw in alpha over here. And you can see, yeah, it really is. We're in the rejection region. So we're rejecting the null hypothesis. But let's keep going. So over here, now everything's t. Everything used to be z, but it's t. See, it says t here. And this is a t score. And all these guys over here are also going to be t's. So it means we have to use all the functions related to t. So this is t dot inverse of the probability and the degrees of freedom, which are here. All right. Now, to copy that, it would be a lot easier if I lock the degrees of freedom. So I'm going to do that. Then copy across. That one's fine. This one is not, because now when we're on the right tail side, remember we have to do the 1 minus the probability, because all the functions look left. So when you're dealing right, you got to adjust that. Then copy this over. Good. And then for our confidence interval, you take x bar there, and then here you take x bar minus the standard error times two-tailed right. Basically, this is how many standard errors. So we want to go 2.05 standard errors away for our confidence interval on the low end. And on the high end, it's going to be that plus the standard error times the two-tailed right. All right. So now we can see our confidence interval here. It is a reject, and lo and behold, the confidence interval does not include the original population mean. Normally we don't expect it to, though sometimes on a one-tailed test it can if they're really close, but it doesn't here. Okay, so then we've got questions. And let me look at these to see if I can help out. I am going to help out with number 3 here. Are the red and black dots at the same height in the first graph? So here's a red dot and black dot. And even though it sort of doesn't look like they are, they actually are. And the reason that we know that they are is because the height of the dot is based upon the standard deviation, right? And we know that these two curves have exactly the same standard deviation because we used this standard deviation of the sample in order to produce the standard deviation of the population. Since we didn't know it, we substituted. And so the answer to this one is going to be same standard deviation, same spread, same height. And I think I'll let you deal with the rest of those. So the conclusion here, you know it's going to be a reject. And you have 2 reasons. One is the PV approach. And so if it's reject, by the way, whenever you see the word reject, if it's reject, then you're saying it's a different population. Remember our initial picture here. If it's a reject, you're basically saying that your sample belongs to not this original blue population, but it belongs over here to the pink population. Okay, so whenever you say reject, you're concluding that it belongs to a different population. So different population, and based upon the probability being small, and different population based upon the test statistic being more extreme. So the interpretation is that it's significantly greater, and the caveat is that we might have made a type 1 error. Okay, so it is significantly greater, but how much greater is it? Remember, percent change 1.5%. So, yeah, 1.5% is significant, but is it meaningful? And that's where this question comes in. The finance department has calculated the new machine is only worth it if efficiency increases by 5%. Well, efficiency only increased by 1.5%, not 5%. So, do not buy the machinery. The alpha threshold was not reached. Well, which one is it? The alpha threshold was not reached, or the percent change was not reached. We'll go with percent change. Though that question might not have been worded the best way possible. Okay. Well, maybe I will help you since this is the first one problem. What do the gray dots represent in the graphs? The gray dots are sample means, and percent change and t-score are ratios with the same numerator. Right? It's kind of cool, right? Percent change, because they both have observed difference in the numerator. So observed difference, observed difference. It's just the denominators are different. Percent change measures magnitude of the difference in the means, and t-score measures if the difference is real. And that actually is the answer. And then finally, in whole numbers, what's the distance in standard errors from the sample mean to each boundary of the confidence interval? Okay, it's kind of a cool question. So, well, in standard errors, remember we multiplied, to get this number, we multiplied by this number. So that's how many standard errors. So it's 2.05 standard errors this way and 2.05 standard errors that way. Well, in whole numbers, 2.05 is just 2. And there we go. You should be all set on this one. And we'll catch you in the next video.